Double slit interference is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now this is the first lesson in a chapter on wave optics, and we're going to encounter interference patterns with light throughout the chapter. And with the double slit interference, this was kind of the first example where it was clear that light was demonstrating these clear constructive and destructive interference patterns common to other waves. And this lent credence to the fact that light has wave-like characteristics. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Now, before we dive into double slit interference, just a quick refresher on constructive and destructive interference. So if you've got two waves that are what we call in phase, where peak lines up with peak and trough with trough, the result is constructive interference. Everything is additive here according to the superposition principle, and you're going to end up with a wave of a larger amplitude, just really the sum of these two amplitudes. If these were equal in amplitude, then the resulting wave would have twice the amplitude. Now the alternative would be 180 degrees exactly out of phase, where peak lines up with trough and vice versa here. And in such a case, assuming they were also equal amplitude, they would exactly cancel, and so 180 degrees out of phase would result in destructive interference. Now it turns out these are the extremes. So perfectly in phase, constructive interference, 180 degrees out of phase, destructive interference, but everything in between is possible as well. So, and as long as they're more in phase than out of phase, you're going to get some degree of constructive interference. If they're more out of phase than in phase, you're going to get some degree of destructive interference instead. So, but these are the extremes, and it's really all we're going to kind of make a note of throughout this lesson. Now, I want to envision another situation that's going to help us kind of understand the double slit interference. And we're going to have two light guns, and somehow these light guns are going to be in phase. Typically, if you had two different light sources, that usually wouldn't work out that way. They wouldn't have what we call coherent light, but we're just going to pretend that they do for a second. So we're going to pretend they're perfectly in phase. And if I took these two light guns and put them side by side, they would fire in phase perfectly. So let's say we fire that second one and we see that it's just going to match perfectly. So, and you have to put up with my artwork here. And so they'd be exactly in phase. Now, what if instead I decided to put one light gun slightly ahead of the other and I started it at this location right here? Well, that would be okay. So as long as I started at exactly one wavelength further ahead of the other light gun, they'd still be perfectly in phase. Or what if instead of that location, what if I decided to start that second light gun at this location right here? Well, that's two full wavelengths ahead of the other light gun. So, and again, as long as it's exactly two full wavelengths, we see they'd be in phase again. And the idea is that one of these light guns, they're arriving at the same endpoint, if you will, but this one has a shorter distance to travel than this one. As long as the one traveling the farther distance is traveling a farther distance by some multiple of wavelengths, then they end up in phase. The contrast would be, what if instead of starting either at the beginning or at where this wavelength starts or this wavelength starts, what if I started exactly at the halfway point in the middle of a wavelength? And so in this case, again, we're going to start with kind of the upswing of the wavelength, if you will. And all of a sudden now we'd see that destructive interference would result. So trough to peak and so on and so forth. So they're exactly 180 degrees out of phase now instead. And the idea is that the difference in the distance the two is traveling is now 1/2 of a wavelength. It's not a multiple of wavelengths, it's exactly half of a wavelength. And so they're exactly 180 degrees out of phase, destructive interference. And that's not the only place I could have started. I could have started at this location right here as well. And now instead of being half a wavelength off, it's now 1.5 wavelengths off, or 3/2 lambda. So, but the result is the same. We still have them exactly 180 degrees out of phase, and destructive interference is going to result. And so it turns out, so when you've got two different light waves, and then we'll find out they don't necessarily have to come from two different sources, but two different places maybe is a better way to look at it. So if they arrive at the same point but travel a different distance to get there, as long as the difference in the distance is a multiple of wavelengths, constructive overlap is going to result. But if it's an odd number of half wavelengths, 1/2, 3/2, 5/2, 7/2 of a wavelength difference, then destructive interference is going to result instead. And that's what we need to take away when we start talking about Young's double slit experiment and double slit interference. So now we can talk about Young's double slit experiment. And ultimately, Young shown coherent light. So typically coherent light is coming from a single source. It's often monochromatic, just a single wavelength, like from a laser. But when he's shown coherent light on the back side of the screen that only had 2 slits where the light could pass through, well, once the light passed through a slit, it spreads out in every direction. But that's going to happen at 2 different places here where it spreads out in every direction, and the light waves coming from either slit now have a chance to interfere with each other. And it turns out if you shine them on a screen, you do see this interference pattern where you see alternating light and dark fringes, we call them. And it's the same interference pattern you see with like water waves and other sorts of waves, which again gave credence to the fact that light has wave-like properties. Now, a couple things we want to define here real quick. So if we start from right in between those 2 slits and draw a horizontal line straight across, so that turns out we define this kind of like the 0-degree point. We're going to define some angles here, and then you can draw angles to any one of the other fringes. So the first dark fringes on either side of it, you could draw an angle right to the very middle of that dark fringe, or you could draw another one right to the middle of that bright fringe. In fact, that's the one we're going to deal with, so that's the one I'm going to draw towards. And then you could draw a lovely right triangle here, but it's this angle right here that we're going to call theta. And we're going to end up forming an equation that shows us how to calculate this angle theta for any bright or dark fringe. All right, now the question would come, well, why do we even have bright and dark fringes? Let's take a look. So let's take a look at the light traveling from these 2 points. And I'm going to use red monochromatic light here in this case. That's why there's light fringes or bright fringes are red and the dark fringes are just dark. And in this case, from the top slit, the light would travel to the center of that bright fringe right there, from the bottom slit to the center right there. And we can see that's a little bit longer journey for the light traveling from the lower slit. Now the idea though is that if the difference in which these 2 light rays travel is a multiple of wavelengths to reach a certain point, then you're going to get constructive interference. But if the distance traveled from the 2 slits is, say, an odd number of half wavelengths, well, then destructive interference would result instead. And that's kind of the idea behind this lovely interference pattern. So we got to figure out a way of kind of looking at this to figure out, well, how much farther did this light from the lower slit travel than the upper slit? And that's going to be a pain in the butt. Now, a couple things we got to define before we get too much further into this. And one is the distance between the slits we're going to call lowercase d. The distance to the screen we're going to call capital L. And all the approximations we're about to derive only really apply as long as L is much, much, much bigger than D, much more so than my drawing shows. And typically that's the way it works. In Young's experiment, I think, D was, the value of D was typically on the order of like a fraction of a millimeter, whereas L was on the order of like meters instead. So in such cases, L was indeed much bigger than D, and the approximations we derived would apply. Okay, so how much further, again, does the light from the lower slit actually travel? Well, here's some of the assumptions we're going to make. So we're going to make the assumption that these 2 lines are parallel. And you might be looking at this and being like, they don't look very parallel, Chad. Parallel lines don't intersect, and those intersect right where they meet, at the bright fringe right there, and you'd be 100% correct. But again, envision the fact that I've had to make D look fairly big, but again, it's usually on the fraction of a millimeter. The distance between those slits is very microscopic, if you will. And then also, the distance to the screen is usually huge, on the order of meters long, again, much wider than even this right here. And all of a sudden, these 2 lines that start out much closer together than you see here, and then travel much farther to reach that common point. So if you just kind of zoomed in on any location along the way, they very well indeed might look parallel in such a case. And that's what we're going to pretend here for a minute. And so what we're going to do is we're going to take this line right here, and we're going to flatten it out to where it actually is parallel with this guy. So, and there's where it goes. If we flatten it out kind of, and we can see the full distance that it travels, and yeah, it's traveling a little bit further than the other one in this case. Now what we're going to do though, is we're going to make kind of a rectangle here. Whoop. And there's our rectangle. Let's get that one out of there. All right, that lovely rectangle should have all 90 degrees. This side should equal this side, and this side should equal this side. And I realize my drawing is not perfect, so you'll just have to bear with me. But that's our rectangle. So, and in this case, how much farther does the low one travel? It's just this little distance right here. So in this little tiny right triangle right here. And it turns out that this angle right here is also theta. The same theta we see right here. And that's a little bit difficult to see, but if you take a look, so if I hold two markers here in a certain angle, like angle theta, and I move them together, as long as I move them together, the angle between them is never going to change. It's going to be still that same angle theta. Well, it's effectively what we're going to do. We're going to take this one right here, which is a perfectly horizontal line, and we're going to rotate it down 90 degrees. And then we're going to take this one right here and rotate it 90 degrees as well. And all of a sudden, that's the angle right in between those two, and it's still equal to theta. That's kind of how we see that. So now we see we've got a right triangle with theta right here. This side of the triangle right here is the distance between those slits, which is d. So, and then we got this one right here. Well, in this case then, so d is the hypotenuse in our lovely right triangle, and this is the short side, the side opposite our angle theta. And if you recall, sine of theta is equal to opposite over hypotenuse, which in our case, sine of theta, the opposite would be this thing we're looking for, which we're going to call delta, the difference in the path length between these two light rays. So, and then the hypotenuse is equal to d, the distance between the slits. And so if we rearrange this just a little bit, we can see that d sine theta is equal to delta, our difference in path lengths. And so that's the key here. What we've really derived here is that the difference in path length between those two light rays is d sine theta. And so now we can see our condition for constructive interference. If the difference in path length d sine theta is equal to a multiple of wavelengths, where m is any integer, so, well, then you're going to get constructive interference. And that is the condition for constructive interference. M here is often referred to as the order. It could be 0, plus or minus 1, plus or minus 2, so on and so forth, any integer value. Now, on the other hand, if d sine theta is equal to some odd number of half wavelengths, and there's a couple different ways we could express that. So the one I'm going to use is m plus 1/2 times the wavelength, where once again m is 0, plus or minus 1, plus or minus 2. What you find out is you plug in m equals 0, you're going to get 1/2 of a wavelength. You plug in m equals 1, you'd get 1.5 wavelengths. Plug in 2, 2.5 wavelengths. You're getting some odd number of half wavelengths, if you will. 1/2, 3/2, 5/2, so on and so forth, which would put the two waves exactly out of phase instead of in phase. And again, this is your requirement for destructive interference. And so now we have a way of solving for theta here. So in one case for the bright fringes, in the other case for the dark fringes as well. So, and that's a common question you might get, is just simply calculating the angular location, if you will, of a certain bright fringe or dark fringe. So you might say, you know, where's the central bright fringe? Well, that's always going to be at 0. And you'd get that if you plugged m equals 0 right into there, and you'd have d sine theta equals 0. So, and the inverse sine of 0 is still 0. So, but for any of the other ones, it's not so intuitive, or at least not something you can just kind of take for granted in your head that it's going to be 0. So, and you'd have to plug in successive numbers of m equals 1. So for the bright fringes on either side, you'd be plugging in m equals positive 1 and negative 1, positive 2, negative 2. Same thing with the dark fringes. It turns out you get the first dark fringes when you plug in m equals 0 here and here, and then m equals plus 1 minus 1 here and here, and so on and so forth, working your way further out. Now, the other thing sometimes you get is, so notice the further back you put the screen, so the more this kind of spreads out and stuff like this. And so some people like to also define not just the angles, but also, if you know this length to the screen, where the center of each bright fringe and dark fringe shows up. So in this case, you'd start from right at the center of your central fringe is kind of ground zero for that as well. And then you just move a certain height in either the positive y or negative y direction. We'll get a couple new expressions here. So these are the expressions for the vertical location here, the height, if you will, of either the center of the bright fringes or the center of the dark fringes. So, and where exactly does this come from? So if you recall, we've got sine theta over here. And also notice we've got this lovely right triangle we constructed to the center of the bright fringe. So let's take a look at that. So we know that one side of this right triangle here is the distance L. That's this leg of the right triangle right here. So the height is what we're now going to call y. So, and we can now make some relationships here. So in this case, notice that tangent of theta would equal y over L. Okay, so tangent of theta equals y over L. Well, it turns out, again, with very small values of d and very large values of L, that any of the thetas you're likely to be looking at here are going to be very small values of theta. So, and it turns out as long as theta is really small, then tangent of theta is roughly equal to sine theta. And so we're going to make, that's another one of the approximations we're going to make here. Let me write that a little bit bigger. So sine theta. So now sine theta equals y over L, again for very small angles of theta. And so if we rearrange this just a little bit, well, going up here, we saw that sine theta was equal to m lambda over d, and we're going to substitute that in. And so here, m lambda over d is going to equal y over L. And if we rearrange this, we solve for y, we see it would equal m times lambda times L over d. M times lambda times L over d. So, and deriving the same one for, or the similar one for the dark fringe would work in principle exactly the same way. And from here, though, these are the four equations, we are ready to do a little bit of plugging and chugging. So we're just going to do a single multi-part question here. And the question says, coherent light, lambda equals 700.0 nanometers, is incident on two slits separated by 0.10 millimeters. At what angles do the first order and second order bright fringes form? If the light is projected on a vertical screen 2.0 meters away, at what height relative to the central fringe do the first order and second order bright fringes appear? All right, so we're looking to solve for both theta, for both the first and second order bright fringes when m equals 1 and m equals 2, and then also to sign for the heights at which they occur again with m equals 1 and m equals 2. But pretty straightforward calculations here. So d sine theta equals m lambda. And in this case, d was given as 0.1 millimeters. Well, 0.1 millimeters, we've got to put that in meters, is going to be 0.0001 meters times sine theta. And again, we want the first order bright fringe. That's where m equals 1. And then lambda here was given as 700 nanometers, which would be 700 times 10 to the negative 9 meters. So we'll divide through by 0.0001 and then take the inverse sign. Let's do that. So we'll call this theta 1 bright equals. So I'll take the inverse sine, parentheses, of 1 times 700 e to the negative 9 divided by 0.0001, close my parentheses, and the angle comes out to 0.40 degrees. Let's see how many sig figs we want here. 2 sig figs, so 0.401, so 0.40 degrees. Okay, so then we want the second bright fringe, which I'll call theta 2 bright here. And in this case, the only difference is that we have to change the value of m from 1 to 2. The rest of the calculation is the same. And so actually I'm going to hit second function and entry and go back in and substitute out the 1 that I plugged in, which I really didn't need to put there, but I knew I was going to do this, and change it for a 2. So, and you can probably predict what this angle is going to be, because essentially this entire side of the equation, once you pull this over, is proportional to m. And so if we just went from m equals 1 to m equals 2, we doubled its value. Well, that's going to double the entire value of that side. When we take the inverse sine here, probably not super surprising that it comes out to 0.80 degrees in this case, 0.802 degrees. All right. So and it turns out that proportionality holds true for small angles pretty well. All right, so there's our angle. Second part of the question says, if the light is projected on a vertical screen 2.0 meters away, at what height relative to the central fringe do the first order and second order bright fringes appear? So this one just has us solving for the y values instead. All right, so in this case, make sure we put everything in SI units once again. Wavelength 700 times 10 to the minus 9 meters. So the length we're told was 2.0 meters. Distance again was 0.1 millimeters, which we could write as 0.0001 or 1 times 10 to the negative 4 meters. And then times this value of m. And in the first case, we're going to plug in a value of 1, and in the second case, 2. So we're going to have y1 bright and y2 bright. All right, what did I do with my calculator? I buried it. All right, we got 700 times 10 to the negative 9 times 2 times 1 divided by 1 e to the negative 4. So for the first one, we're going to get 0.014 meters. So in this case, we're not even taking an inverse sign. If you plug in a 2 for the value of m, you're doubling the value of m. You'll double this entire side of the equation, and you should therefore get 0.028 meters. But I'll go ahead and plug it into my calculator. Second function entry brings up the entire last equation I put in there. And instead of multiplying by 1 at the end, I'm going to replace that with a 2. And lo and behold, it comes out to exactly 0.028 meters. And that concludes our plugging and chugging. If you found this lesson helpful, consider giving it a like. Happy studying.